Since we've talked about light in so many different courses, I'm going to just have a brief review of light, and I'll appeal back to your knowledge from general chemistry and from physics and from high school and anywhere else that you've learned about light up until now. So let's go ahead and take a look at some of our main equations, after which we'll take a look at our wavelength ranges, the names of those different ranges, and also a few things about what's happening on a molecular scale. All right, so our main equations for this, we're going to have the speed of light, and speed of light is going to be in units of meters over seconds, equals, and we're going to have our frequency, which is given by the variable nu, and that's going to be in units of 1 over seconds. And you can see from that, that means that the other thing we'll have to account for is meters. That will be from our wavelength, which is given by lambda, and that will be in units of meters, at least for them all to work together nicely. Now, of course, we can still go ahead and convert from nanoseconds into seconds. We can still convert from nanometers into meters, all of those fun things. And so that's how we're typically going to be seeing things work. In fact, the commonly used wavelength range ends up being nanometers, so we're going to do that conversion a heck of a lot. And I'll have a little more to say about nanometers and why we end up working in nanometers so much instead of working in units of meters. So I'll bring that up here in just a minute. Now this is going to be one of our core equations. Now the next one is going to be just converting that frequency into an energy. So for that we're going to use Planck's constant, which is h, and we're going to use frequency once again in units of 1 over seconds. Now notice we have to get from something containing seconds information into some sort of an energy unit. Planck's constant is going to contain that. I also want to caution you though, when you go to look up Planck's constant, be very careful to actually look up Planck's constant, because you'll often see that there's also a version given that has a bar across it, often referred to as h bar. Don't use that one. That one appears in a lot of physical chemistry work because it ends up accounting for some really common constants, and that's as far down that rabbit hole as I'm going to go. I'll point at it and say don't use it, and leave it at that. So Planck's constant is going to be 6.626 times 10 to the negative 34, and the units on that will be joules seconds. So notice that when we have that multiplied times our frequency, seconds cross cancels, leave us in units of joules, which means that natively we're going to end up in joules from this equation. We'll typically going to have to convert into kilojoules or kilojoules per mole if we want to actually have that into a more common scale. So be aware of that and be careful about that conversion. Just remember that initially you're going to be finding out the energy of one photon. If you make it for an entire mole of photons, you'll have to multiply times plus Avogadro's number. So yeah, you'd multiply by that and you'd end up getting per mole. All right, now one other thing I'll point out, the book and lots of other books love to give you a combined form where you just substitute frequency. So you rearrange that everything's equal to frequency, substitute that into this equation, and then you end up getting this equation, which is pretty useful because we work on lambda so often, and nanometers so often, so you don't have to do any extra conversions. That said, despite the fact that my PhD and all of my work since then has been using light, I still have not taken the time to just flat out memorize this because it's so much easier to just plow through and quickly calculate everything on the fly. I don't really see a big point in having a third piece memorized if your memory is poor. If your memory is good, however, it'll save you a lot of time. Now, you probably remember for organic chemistry, we worked in wave numbers a lot when we did infrared. Well, we can also just say, well, this 1 over lambda, that's nice, but how about we just go ahead and get that to be a different term? And that's going to be wave numbers. So it'll be h times c times, now they keep the nu to make it clear that this is kind of like frequency, but they put the tilde over top of it to say, yeah, but it's not frequency, it's wave number. The reason that we like doing that is now energy is going to be proportional to wave number, but it's not going to be in the same unit and same format as we'd have for frequency. So make sure you're being very careful about whether you're looking at frequency or wave numbers if you're doing those kind of conversions. I typically don't work in wave numbers at all, but it really depends on what specialty in the field you're in. Okay, so that's what I want us to be reminded as far as the equations go. Let's take a look at our spectrum. Now, remember that on the wimpy side, energetically, we're going to be at radio. You can see that radio is going to have a small number of kilojoules per mole of photons. Remember, a mole of photons is going to be 6.022 times 10 to the 23rd photons divided by 1 mole. That's a conversion that throws people a lot of the time when they go to do it. So we're talking about weak energies at this point. As you get more and more energetic, you are going through the microwave range, then finally into the infrared, and then finally the visible, ultraviolet, X-ray, and gamma ray. Now, if you have to just remember that quickly, I'll point out we know that these are the high energy rays. These are going to be high frequency as a result. They're also going to be very tiny wavelengths for X-rays and gamma rays. If you have to remember that radio ends up having really long wavelengths, just keep in mind that these things have to have long enough waves that when they hit into a mountain, the oscillation still has parts of the wave on both sides of the mountain, so could at least. And so it's ending up having a much better penetration factor for things like buildings and all that than you'd have for X-rays or gamma rays. Made it really useful for communication. Now, let's hunker in here on what exactly is happening in each. So, when we dial in, really wimpy energies, all we're doing is getting the molecule to spin. And that should make some sense because we're not doing anything to change any potential. We're just giving it some kinetic energy when it starts spinning. When we start doing vibration, keep in mind that we're stretching the bond. And if you remember what the bond energy looks like, remember there's kind of a sweet spot right here at a certain bond length. If you press it any closer, it starts repelling because you have the nuclei getting too close together. If you start stretching it apart, you're starting to have to put in enough energy to do that stretching motion until eventually you get them pretty much dissociated. And so this will gradually approach some constant value as you get to radius equals infinity, though of course in reality we never have to care about it getting that far away. Now, that means that you're going to be staying in some certain well down here for vibration. And that's not going to be a giant energy range. And it's going to be significantly less than what we're talking about for making bonds or actually getting electrons to excite. Now, one thing that we don't talk about as often as I'd like in Gen Chem is our most high-end level of what's actually happening on the molecule. We can actually think of molecular orbitals. So the orbital of the electron around the entire molecule. And what ends up happening is we can promote an electron from one orbital to a different orbital. And it turns out some of these actually end up being what we call antibonding orbitals, where we've actually made the electron choose to be on one side or the other more often. It can still tunnel through this gap in the middle, but you don't have that density in the center helping hold it together necessarily. That just depends on which one of these orbitals you're in. But as you put an electron from these ground levels to these higher levels, you're actually promoting the electron and you're changing the strength of some of the bonds. That doesn't mean you've broken them, but you're starting to fiddle with them a little bit. However, you put in more energy than just messing with them a bit, you're actually going to be talking about the energy to make and break bonds, and that's happening out here in our X-ray regime. So make sure that you're aware of what's happening in those ranges. Now let's also come to the visible spectrum. Obviously it's easy to remember that infrared goes right up against red, and ultraviolet goes right up against violet. But sometimes, just because we're so used to thinking red, orange, yellow, green, blue, purple, the whole Roy G. Biv, if you like indigo, we sometimes just want to start writing red following numeric order, but we don't actually have that be correct. Red is going to be something like 650 nanometers. Now you'll notice that we're being very generic and crude in our placement here, and that's intentional. We really have to be, because different pigments and concentrations in people's eyes let them see just a little bit further into the range than other people's. So violet, we typically say, is something like 4 to something like 450. 450 to 500 is blue. Green is the bottom half of the 500s, heading toward the upper, maybe the top third of this 500 range. We're in yellow and orange, and then finally we get into red, and then out into the infrared. Okay, so just a quick reminder of what's going on as we look at our spectrum.